Welcome to Chapter 11, Anchorages. Before we get into the details, let's set the stage. Anchorages are the foundation of every rope rescue system. Without a strong, reliable anchor, everything else we do in rigging is at risk. So, what's the goal of this chapter? You'll learn how to identify suitable anchor points in any environment, evaluate their strength and reliability, properly configure anchors to safely manage loads and forces. Think of anchors like the roots of a tree. No matter how strong the branches or ropes are, if the roots aren't solid, the whole system can fail. Here's a mantra to keep in mind. Anchor first, rig second, check always. Take your time, analyze every option, and make decisions based on both science and experience. Anchor system terminology has evolved differently across industries. That means the words we use in the field can be confusing. A rescuer must familiarize themselves with the proper terminology to minimize miscommunication and keep operations safe. Well-constructed anchorage is one of the most important building blocks in rope rescue. If you lack suitable anchors, the ropes, hardware, and even the rescue team are at risk. Secure and appropriate anchor points must be established before rigging the rest of the system. That's why it's critical to understand the types of anchor systems available, when to use each, and the hazards associated with them. We'll also explore NFPA integration as we go, including NFPA 1006, 1983, 1670, and 2500, so you'll see how these standards guide anchor selection, rigging configurations, and safe operational practices. And one more thing, anchors aren't just metal bolts or trees. Rocks, boulders, structural beams, and even vehicles can serve as anchors, but only if they are properly evaluated. So, take a deep breath, focus on the fundamentals, and let's get anchored. All rope rescue systems, no matter how simple or complex, must incorporate a solid, well-constructed anchorage. Think of it as the foundation of a building. Without a strong base, everything else you build is at risk. The best anchorages aren't just strong, they're well-positioned. They must be placed so that they support your objective, whether that's lowering a patient safely, hauling equipment, or creating a safe access line. And strength alone isn't enough. The anchor must also be stable. It needs to handle the intended load without shifting, moving, or failing under pressure. Here's the hard truth. Without suitable, secure anchors, the rest of your rope rescue system is in danger. It doesn't matter how well you rig your ropes, how solid your knots are, or how experienced your team is. If the anchor fails, the entire system can fail. So, as we move forward, always remember this guiding principle. Anchor first, rig second, check always. Everything else depends on it. Now let's talk about anchor terminology, because this is where things can get a little confusing. When we talk about anchors in rope rescue, we often hear the terms natural and artificial. These words came from recreational climbing and mountaineering, and over time, the terminology has evolved differently in different industries, which is why it can feel a bit messy. A natural anchor is something that's left intact after use, like a big tree, a sturdy boulder, or a rock outcrop. You set your rope on it, use it to support a load, and then walk away, leaving the anchor where it is. An artificial anchor, on the other hand, is something installed specifically to hold your rope, and is usually removed afterward. This could be a chock, a climbing bolt, or other temporary hardware. Over time, the lines between these two categories have started to blur. Climbers began leaving slings on rock protrusions, and bolts were installed in permanent positions. Meanwhile, in the full protection and industrial world, anchor concepts were evolving with an eye toward training requirements, system reliability, and regulatory compliance. The key takeaway? Whether natural or artificial, the anchor must be strong, reliable, and appropriate for the environment and task at hand. Don't get stuck on the terminology. Focus on the principles of safety and load management. Now that we've talked about natural and artificial anchors, let's look at permanent and temporary anchorages. In the world of occupational safety, two key organizations, OSHA, the Occupational Safety and Health Administration, and ANSI, the American National Standards Institute, have established terminology to make sure we're all speaking the same language. They distinguish between permanent anchorage, something that's installed to stay in place for repeated use. Temporary anchorage, something installed for a specific operation and removed afterward. Here's the important point. Installing and using temporary anchorages requires more training and experience than clipping into an existing permanent anchorage. So, while both types can support a rescue, the skills and judgment needed are different. For our purposes, and to stay consistent with OSHA and ANSI, we'll use the following terms. Anchorage, or anchor point, is a single secure connection for an anchor. One anchor point might be used alone, or combined with others, to create a full anchor system capable of safely supporting the expected load in a rope rescue operation. Anchor points can take many forms, from structural beams, trees, boulders, or even vehicles, as long as they meet the strength and stability requirements. An anchor system is one or more anchor points rigged together to provide a structurally significant connection for your rope rescue system. Think of it as the foundation of your setup. The anchorage connector is the method or device you use to attach your rope system components to the anchor. Carabiners, slings, shackles, or other hardware all fall under this category. For clarity and precision, rescuers should use the full terms, like anchor point or anchorage connector, instead of just saying anchor. It might seem like a small detail, but using the correct terminology helps prevent miscommunication. And in rescue operations, that can make all the difference. Remember, permanent or temporary, anchor points are the foundation of safety. Know what you're connecting to, and connect correctly every time. Time to talk about anchor strength, one of the most critical factors in any rope rescue system. Anchorages must be able to sustain the maximum anticipated load, plus a safety factor. In simple terms, they have to be bomb-proof, meaning their strength far exceeds any force your rope system could possibly generate. There's no magic number for anchor strength. It's really a judgment call made by the rescuer, based on experience, training, and the specific environment. But the goal is always the same: withstand the maximum expected force times and appropriate safety factor. So, what affects anchorage strength? A few key things. Condition of the anchorage. A live tree can usually take more stress than a dead one. Structural nature. A load-bearing column in a building is far stronger than a handrail. Location of force. Pulling near the base of a tree is stronger than pulling higher up. We also classify anchors into 3 practical categories. Great anchors. These are so strong that one is enough to hold your system safely. Good anchors, solid anchors, but you might want 2, one for each system, to ensure redundancy. Poor anchors. Weak or unpredictable anchors. You may need 2, 3, or even 4 tied together to achieve the same strength as a single good anchor. Remember this mantra: anchor smart, not just strong. It's not just about raw strength. It's about using the right anchor in the right way and building redundancy when necessary. One of the most important things to understand about anchors is the direction in which the force is applied. The specific direction of a vector can greatly influence the strength of an anchor. Here's the key idea. An anchor system that is strong in one direction may not be strong in another. That means you can have a bomb-proof anchor in one orientation, but it could weaken significantly if the pull changes. So, always try to set anchor points in line with the expected direction of pull. Think of it like pointing the tip of a wedge in the direction you want the force to travel. Also, consider what happens if the direction changes during the rescue. For example, the pull might shift due to a change in the fall line, or the difference between raising and lowering a load. In some placements, a change in pull direction can reduce the effectiveness of your anchor, or worse, cause it to fail. Take your time, analyze the vectors, and make sure your anchor is set to handle the forces exactly where they're going to act. Anchor with the pull in mind, and your system will stand the test. Where you place your anchor system can have a big impact on the stability and safety of the rescue. Generally, an anchor system that is close to and directly above the subject provides the most stability. This positioning makes edge transitions smoother and makes loading the subject safer and more controlled. That said, there are situations where it may be better to place an anchor off to the side. For example, a rocks or other debris could fall on the subject or rescuers. Obstacles exist between the anchor and the subject that could endanger the team or damage equipment. A fire or other hazard is present near the rescue area. The environment or people in the area are hostile. There simply isn't a suitable anchor directly above. Sometimes it's also smart to preset additional systems off to the side, such as a separate haul system or a non-loaded belay line. This provides adequate working space and helps avoid rope entanglement. Finally, always be aware of the angles between your systems. Poor angles can drag debris over the edge or create swingfall hazards. Techniques like directional deviations or rebelays can help manage these risks when necessary. Most rope rescue anchor systems are made up of 2 subsystems. The first is the working system, which actually moves the load. The second is a backup system, sometimes called a belay, which protects against potential failure. Ideally, each system should be anchored independently. That said, sometimes rescuers may connect the working system anchor to the backup, or vice versa, just for added security. Anchor systems have a number of potential points of failure. These include uncertain strength of anchor points. This is one of the most common causes of anchor failure. Human error, selecting a poor anchor, tying knots incorrectly, or leaving carabiner gates unlocked. Equipment failure, rope or webbing abrasion, cutting, or hardware stress can compromise the system. Because the rest of the rope rescue system depends on the anchor system, it's good practice to always back up your anchors. This redundancy is your safety net and can prevent a small mistake from becoming a serious incident. Backing up is all about adding redundancy to anchor systems to improve safety. There are two primary methods for backing up an anchor: using the same anchorage or using a separate anchorage. First, backing up to the same anchorage. This method should only be used if you are absolutely certain the anchorage is bomb-proof, strong enough to sustain any forces the rope rescue system might put on it. Using the same anchor for backup is usually done when there is concern about other components of the anchor system, like carabiners, knots, or slings, potentially failing. Second, backing up to a separate anchorage. This method requires multiple anchor points that are independent of each other. When the direction of loading may shift from side to side, the multiple anchorages should be configured for load sharing to distribute forces effectively. Properly backing up your anchors reduces the risk of system failure and gives both rescuers and subjects a much safer outcome. Remember, redundancy in anchor systems isn't optional. It's a critical safety principle in rope rescue. The method of backing up an anchor system and the number of anchor points you need depends on several important variables. Let's break them down. First, the condition of the anchor points. If there is any potential for failure of an anchor point or of the equipment attached to it, you will need more than one anchor point. Second, the nature of the rope rescue operation. If both a main line and a belay line are being used, you should consider separate anchor systems for each. Using the same anchor for both lines can create dangers like rope tangles or heat fusion damage if the ropes cross. The belay system also needs to be substantial enough to arrest a fall, which usually means adding a second strong anchor. Third, the loads and stresses involved. The forces on an anchor system vary depending on how it is used, such as supporting only equipment, supporting the weight of one person, creating directionals that amplify the load, withstanding shock loads from a fall or partial system failure, supporting rescue lowering operations, operating hauling systems, maintaining highlines, where a rope is suspended between 2 points to move people or equipment. In short, the stronger and more redundant your anchor system, the safer your operation. Every variable matters, so always assess the condition, nature, and loads before committing to a setup. One of the most critical responsibilities during any rope rescue operation is to monitor your anchor systems continuously. Why? Because loads shift, ropes move, and equipment wears, and even the strongest anchor can become less secure over time. Keeping a constant eye on the system ensures your safety, the safety of your team, and the safety of the rescue subject. Remember, an anchor is not set it and forget it. Stay alert, check the system frequently, and adjust as needed throughout the operation. It's important to understand the difference between an anchorage and an anchorage connector. First, an anchorage is only useful if you can attach to it effectively. For example, a stairwell beam or a large boulder might be strong enough to serve as an anchor, but it won't help you unless you can connect your rope and hardware to it securely. Next, we have anchorage connectors. These are artificial devices designed to create temporary anchor points, or to provide protection in places where natural anchors aren't available. Examples include straps, carabiners, portable beam clamps, and removable bolts. Many artificial connectors are also designed for use in rock, such as bolts, nuts, chocks, and cams. However, for these devices to be safe and effective, they must be placed by someone skilled and practiced in their use. Improper placement can turn a potentially strong anchor into a dangerous point of failure. In short, a strong anchor alone isn't enough. You must be able to connect to it safely using the right tools and techniques. Before we commit any rope rescue system, we must assess each potential anchor carefully. The safety of the team, the subject, and the integrity of the system depends on this step. First, consider the strength of the anchor. Ask yourself, Can this point withstand the maximum load we might put on it, plus a reasonable safety margin? Remember, we're not just looking at static weight. Think about dynamic forces from raising, lowering, or a potential fall. Next, evaluate the stability and condition of the anchor. Is it solid? A live tree usually provides better security than a dead one. A structural beam may be strong, but is it corroded or loose? Look carefully for cracks, rot, rust, or any signs that the anchor could fail under stress. Placement matters, too. Make sure the anchor is positioned so that the force is applied in a direction it can handle. If the pull is likely to change direction during the operation, consider using directional anchors or presetting multiple anchor points to share the load. Then, check the connectivity. Can you attach your rope and hardware effectively? If it's a natural anchor, is there a way to wrap a sling or webbing safely? If it's an artificial anchor, has it been installed properly by someone trained in its use? Finally, consider redundancy. Even if an anchor looks strong, adding a backup system increases safety. 2 independent anchors are better than 1, especially in situations where loads could shift or where the forces are unpredictable. Always remember, assess first, attach second, load last. Take the time to observe, test, and think through every anchor before committing your ropes or equipment. A careful assessment at this stage can prevent failures later that might put everyone at risk. In summary, effective anchor assessment requires you to evaluate strength, stability, placement, connectivity, and redundancy, and to combine these factors with experience and sound judgment. When in doubt, build redundancy, move slowly, and stay aware of your surroundings. Let's dig into single-point anchorages. At its simplest, a single-point anchor is just one anchor being used as the primary support for the entire rope rescue system. According to Jones and Bartlett's Principles of Rope Rescue, 5th edition, this is the most straightforward style of anchoring, and you'll see it taught the same way in the CMC Rope Rescue Manual, the NPS Rope Rescue Manual, and CAL FIRE's Rope Rescue programs. Now, there are 2 main ways we build a single-point anchor. 1. Direct connection, where the rope itself is tied or clipped directly to the anchor. Think of wrapping a tree with a tensionless hitch, or clipping directly into a steel beam with carabiners. 2. Indirect connection, where we use another piece of equipment as a connector. That might be a length of webbing, an anchor strap, a beam clamp, or even a tripod leg. The rope attaches to that connector, which then transfers the load back into the anchor. From a standards perspective, NFPA 1006 and 1670 both emphasize that anchor systems at the operations level must be capable of supporting the loads anticipated in rescue. NFPA 2500, the updated standard that merged 1670/1983/1858, reinforces that anchors must be chosen and built with redundancy and strength in mind, even when using just a single point. Sprat training echoes this too. If it's a single point, it had better be bomb-proof. Now, here's the trade-off. Single-point anchors are fast, simple, and efficient. Less rigging, fewer components, less chance for confusion. But, and it's a big but, if that one anchor fails, the entire system fails. So when we go with a single point, we have to be absolutely certain it is solid. No rot, no cracks, no questionable strength. If there's any doubt, build redundancy into it, or shift to a multi-point system. Light-hearted note. The manuals always call for a bomb-proof anchor. I've never seen a bomb-proof stamp on a tree or a car axle, so really it's up to us to make the judgment call. If you wouldn't hang your pickup truck from it, don't hang your rescuer from it either. So, key takeaway here: simple, fast, but unforgiving if you choose wrong. Single-point anchors require good judgment, and the standards back that up. Pick it right, check it twice, and then trust it. Now let's talk about one of the simplest and strongest anchors we can build, the tensionless hitch. The tensionless hitch is considered a go-to choice in urgent situations. Why? Because it's fast. Time is critical in rescue, and this hitch lets us set up a strong anchor with minimal equipment. Here's the basic idea. Instead of tying a knot in the rope, you just take the standing end and wrap it around your anchor several times. Each wrap builds friction, and the load is transferred directly into the object you're anchoring around. Let's hit the advantages. It's simple, fast to build, easy to teach, and fewer moving parts. It reduces stress on the rope and hardware. Because we're not cinching a knot in the loaded section, the rope retains nearly 100% of its strength. It's adaptable. If conditions change, it's easy to add or remove wraps to adjust friction. The benefits are important to highlight. With enough wraps, essentially all the force is applied to the anchor object. Each successive wrap takes less and less tension, so the system equalizes itself. Because there's no knot in the loaded rope, you avoid the strength reduction that knots typically create. The anchor object should be at least 4 times the rope diameter to prevent a sharp bend that weakens the rope. There's also an alternative approach worth mentioning. Instead of finishing with a figure 8 and carabiner, you can tie off the end with a hitch or knot that locks the wraps in place. The key is to make sure the rope can't unwind itself, and that no bend is introduced into the loaded line. NFPA 1006 and 2500 both note that rescuers at the operations level need to demonstrate the ability to construct strong anchors quickly. The tensionless hitch is a textbook example of meeting that requirement. When you need an anchor fast, and you've got a strong, round anchor point available, the tensionless hitch is hard to beat. Simple, efficient, and it keeps your rope at full strength. Now let's talk about using knots themselves to make an anchor. This method is as straightforward as it sounds. You take your rope, wrap it around the anchor point, and then finish it off with a knot. This setup works well in situations where you don't expect to move or adjust the anchor during the rescue. For example, if you've got a short vertical member like a post or a beam, you can tie a figure 8 on a bight and drop that loop right over the top. If the anchor is larger or shaped in a way that makes that difficult, you can wrap the rope around it and secure it with something like a figure 8 retrace or a bowline. There are a couple of things we have to keep in mind with this approach. First, knots reduce rope strength, anywhere from 20 to 30% depending on the knot. That's not enough to rule them out, but it's something you need to factor in when you're analyzing the system. Second, the angle of the loop you're tying matters. If it's too wide, you start to distort the knot and put extra force into the rope and the anchor. Keep those angles neat and narrow, so the knot holds its shape and the forces stay balanced. The other limitation here is flexibility. If you tie your main line directly into the anchor, it makes it much harder to adjust things later. And rescues are dynamic. Conditions can change quickly. If you've locked your main line into the anchor with a knot, you may find yourself having to rebuild more than you'd like. A common workaround is to build the anchor with a separate piece of rope or webbing that's at least as strong as your main line. That way your main line can clip into the anchor system cleanly, and you keep the option to adjust things if the situation changes. So, knots are absolutely a valid way to create an anchor, simple, effective, and sometimes the best choice, but you've got to weigh the loss of strength and the reduced flexibility before you commit to it. Now let's talk about using knots themselves to make an anchor. This method is as straightforward as it sounds. You take your rope, wrap it around the anchor point, and then finish it off with a knot. This setup works well in situations where you don't expect to move or adjust the anchor during the rescue. For example, if you've got a short vertical member like a post or a beam, you can tie a figure 8 on a bight and drop that loop right over the top. If the anchor is larger or shaped in a way that makes that difficult, you can wrap the rope around it and secure it with something like a figure 8 retrace or a bowline. There are a couple of things we have to keep in mind with this approach. First, knots reduce rope strength, anywhere from 20 to 30% depending on the knot. That's not enough to rule them out, but it's something you need to factor in when you're analyzing the system. Second, the angle of the loop you're tying matters. If it's too wide, you start to distort the knot and put extra force into the rope and the anchor. Keep those angles neat and narrow, so the knot holds its shape and the forces stay balanced. The other limitation here is flexibility. If you tie your main line directly into the anchor, it makes it much harder to adjust things later. And rescues are dynamic. Conditions can change quickly. If you've locked your main line into the anchor with a knot, you may find yourself having to rebuild more than you'd like. A common workaround is to build the anchor with a separate piece of rope or webbing that's at least as strong as your main line. That way your main line can clip into the anchor system cleanly, and you keep the option to adjust things if the situation changes. So, knots are absolutely a valid way to create an anchor, simple, effective, and sometimes the best choice, but you've got to weigh the loss of strength and the reduced flexibility before you commit to it. Next up are pre-sewn slings. These are loops of webbing that have been professionally sewn and rated by the manufacturer, and they've become one of the most common anchoring tools in rope rescue. The big advantage here is convenience. They're fast, they're simple, and they remove a lot of the guesswork. Instead of tying webbing into a loop yourself, you've already got a finished product that's strong and ready to clip in. That also eliminates the chance of tying the wrong knot, or having a water knot start to work loose over time. Pre-sewn slings come in a wide variety of lengths and widths, which makes them very versatile. You can carry a small set on your harness or in a team cache, and almost always find one that fits the anchor you're dealing with. When it comes to buying them, there are a few things to keep in mind. First, make sure the sling has the tensile strength you need for rescue operations. Manufacturers rate these slings differently depending on how they're used. Straight pull end to end, basket hitch around an anchor, or girth hitch. Always look at those ratings, and make sure they fit within your safety factors. And stick to companies that test and certify their products. This isn't the place to cut corners. Finally, inspection is key. Before and after every use, check the stitching and the webbing itself for wear, cuts, burns, or frays. If the sling shows damage, retire it. Webbing is strong but unforgiving. Once it's compromised, it's no longer safe to use. So, pre-sewn slings give us a quick, reliable, and tested option for anchor connections. They make life easier in the field, but like everything else in rope rescue, we need to use them with awareness and keep up on our inspections. Now let's move into anchor straps. These are lengths of webbing that have hard rings sewn into each end, and they're designed so you can clip in with a carabiner. They're quick, they're reliable, and they've become a standard option for building anchors. Anchor straps are available with different strength ratings, which are defined under NFPA 2500. The heavy-duty versions, marked with a G designation, usually have an end-to-end breaking strength around 8,000 pounds. That's about 35 kilonewtons. The lighter-duty versions, with a T designation, run closer to 5,000 pounds, or about 22 kilonewtons. Both are strong enough for rope rescue applications, but you always need to select the strap that matches your safety factors. Now, the actual strength can change depending on how you rig the strap. If you run it in a basket configuration, you often get higher strength, but that's not guaranteed. If the angle between the two legs is too wide, you can actually reduce its capacity, sometimes even below the straight end-to-end rating. If you rig it in a choker configuration, strength is always reduced, especially if the choke angle is tight. That's why it's important to pay attention to those internal angles and rig them properly. NFPA also makes a distinction between simple end-to-end straps and multi-configuration straps. Only the multi-configuration versions are required to report strength ratings for basket and girth hitch setups, so make sure you know what you're working with. Some straps even come with adjustable buckles, so you can size them to different anchors. Those are handy, but remember, the buckle can slip under load, and the slip strength may be lower than the strap's overall rating. Always check the manufacturer's specs. Beyond anchors, these straps can also serve other purposes. For example, as a quick litter bridle or as a handy connection point for an edge attendant. That versatility is one reason a lot of teams carry them. Just like with other pre-sewn gear, every strap must be inspected before and after each use. Look for frayed stitching, cuts, burns, or any sign of wear that could compromise its strength. One problem you'll run into is that a simple loop of webbing on a vertical anchor likes to slip downward. To fix that, we have a few techniques. The basket hitch is one option we've already discussed. The girth hitch is another, but be careful. The temptation is to cinch the webbing back on itself, and that puts dangerous stress on the fibers. Don't do it. A better option is the wrap 3, pull 2 system. With this, you wrap 3 times around the anchor and pull 2 loops forward for your connection. It's stronger than a girth hitch and tends to stay in place better on vertical anchors. For maximum strength, always position the webbing not on the inside loop, so it carries the least stress. So the takeaway with anchor straps is this. They're strong, versatile, and fast, but you've got to rig them correctly and match them to the job. Pay attention to how the configuration affects strength, and you'll get a solid, safe anchor every time. When we're using webbing or anchor straps, one of the most secure ways to attach to an anchor is to tie the webbing into a loop around the anchor point with a ring bend knot. That knot, also known as the water knot, is strong, simple, and reliable when tied and dressed correctly. That said, there's a practical limitation. If the anchor object is very large, let's say a big tree trunk or a wide concrete column, getting the webbing around it and tying the knot in place can be awkward. It can also be time-consuming, especially if you're working by yourself. An alternative is to take the webbing, tie it into a loop first, and then wrap that loop around the anchor. Once it's in position, you can simply clip the 2 sewn ends together with a carabiner. It's fast, and it avoids the struggle of tying the knot while reaching around a large anchor. The trade-off is that this method requires twice the amount of webbing compared to using an untied piece. Since you're closing the loop before you wrap it, you'll need a longer sling to make it work effectively. So, the choice comes down to the situation. If the anchor is small or manageable, tying the webbing around it with a ring bend knot works great. If the anchor is large or awkward, pre-tying the loop and clipping it back into itself is often the easier solution. Just make sure you've got enough webbing to do it safely. On this slide, we're looking at another secure method for using anchor straps. The most direct option is to take the strap and tie it into a loop right around the anchor point. We use a ring bend knot, also called a water knot, to close that loop. Once it's snugged in place, you've got a solid, reliable anchor connection. But there's a catch. If the object you're anchoring to is very large, tying the strap directly around it can get awkward fast. Trying to hold the strap in place and tie the knot, especially if you're working alone, isn't always efficient. That's where an alternative method comes in. Instead of fighting with the strap around the anchor, you tie the strap into a runner first, creating a loop. Then, you wrap that loop around the anchor and clip the sewn ends together with a carabiner. This method is quicker and often easier to manage when you're dealing with large or bulky anchor points. The trade-off is that you need more strap length. Because you're doubling it back on itself to make that loop, you'll use up twice the material compared to a single length tied around the anchor. On this slide, we're looking at another secure method for using anchor straps. The most direct option is to take the strap and tie it into a loop right around the anchor point. We use a ring bend knot, also called a water knot, to close that loop. Once it's snugged in place, you've got a solid, reliable anchor connection. But there's a catch. If the object you're anchoring to is very large, tying the strap directly around it can get awkward fast. Trying to hold the strap in place and tie the knot, especially if you're working alone, isn't always efficient. That's where an alternative method comes in. Instead of fighting with the strap around the anchor, you tie the strap into a runner first, creating a loop. Then, you wrap that loop around the anchor and clip the sewn ends together with a carabiner. This method is quicker and often easier to manage when you're dealing with large or bulky anchor points. The trade-off is that you need more strap length. Because you're doubling it back on itself to make that loop, you'll use up twice the material compared to a single length tied around the anchor. Portable anchorages are prefabricated or movable systems that we can place where we need them. They can serve as a primary anchor point or act as a directional aid to route the rope more efficiently. In the fire service, some of the most common portable anchors are vehicles. A fire engine or heavy rescue truck can make an excellent anchor if it's positioned correctly. The weight of the apparatus gives us confidence, but only if we take steps to stabilize it. Set the parking brake, drop the transmission into park or neutral in no part, and chock the wheels. But here's where judgment comes in. A vehicle is only as solid as the surface it's sitting on. If that engine is parked on ice, mud, loose gravel, or a slick slope, it can slide or shift under load. Conditions can change quickly. What looked secure when you arrived may not be secure 5 minutes later. So part of our job is not just picking the anchor, but constantly evaluating whether it remains reliable as the scene evolves. Another strong option is using heavy objects like concrete jersey barriers. These are designed to resist movement and can provide a very stable anchor when nothing else is available. Again, the environment matters. If the barrier is on unstable ground or could be tipped by the load, it's not as solid as it looks. We also have purpose-built portable anchors like tripods, bipods, or edge rollers. In some cases, these act as the main anchor, such as a tripod over a manhole. In other cases, they simply redirect the rope to avoid edge damage or to get a cleaner line of pull. So the big idea here is this. Portable anchors give us flexibility, but we can't just assume weight equals safety. Evaluate the conditions, stabilize what you're using, and keep asking yourself, is this still solid right now? We're going to chat about some of the most common types of portable anchorages you'll run into on rescue scenes. The first is the tripod. A tripod can serve as a complete standalone anchor system, often set up over a confined space like a manhole cover. It can also be used as a high directional, which helps manage the angle of the rope and keeps the load from rubbing against edges. Tripods aren't the only option. We also see monopods, bipods, and even quadpods, all variations that can be adapted to the space and the load. Next up is the beam clamp. This is a quick option when you're working in an industrial setting with steel structures. You can attach it directly to a beam, and some models are rated to meet ANSI, CSA, and OSHA standards for one-person loads. That's about 5,400 pounds or 24 kilonewtons. For heavier systems, you can rig multiple clamps together as a multi-point anchor to meet your safety factors. Another tool is the removable bolt. These anchors can be very useful, but they require prep. You need a hole of the correct depth and diameter, drilled into solid material. The bolt itself has to be the right size and type for the load you're expecting. If the hole or the bolt is mismatched, you won't get enough holding power. They're not an everyday anchor, but in the right scenario, they're a very effective option. Finally, we've got the picket system. This is especially valuable in natural areas where there aren't strong trees, boulders, or structures to tie into. Pickets can be driven into soil or snow, depending on the conditions. When rigged properly, a series of pickets tied together can create a very solid anchor. But here's the key. It requires training and time to set it up right, and it won't work in every soil type. Loose sand, soft mud, or certain types of snow won't hold securely, no matter how many pickets you use. Most reliable picket systems use multiple rows tied together to share the load. So the big picture with portable anchors is this. They expand our options. Whether it's a tripod over a manhole, a beam clamp in a plant, a removable bolt in solid rock, or a picket system in an open field, each tool has its place. The job is to match the anchor to the environment, the load, and the safety factors we need. Okay, let's chat about the rigging plate. This little piece of aluminum might not look like much, but it can make a big difference in keeping your anchor systems clean and manageable. One of the biggest advantages of a rigging plate is organization. Instead of clipping every rope, pulley, or carabiner directly into the anchor strap or master point, which can quickly turn into a cluster, the rigging plate gives each component its own spot. That keeps the system clean, easy to follow, and safer to manage. It also helps to spread components out so they're not jammed together. When gear is stacked on top of each other, it's harder to see what's connected where, and it can be more difficult to troubleshoot or adjust under load. A rigging plate keeps everything visible and spaced out. Another benefit is that it allows you to bring multiple anchor points together into one master point. For example, if you've built a multi-point anchor using 2 trees, you can clip each side into the rigging plate and then have one clean master connection for the main line. And it works the other way too. A rigging plate lets you disperse multiple lines from a single anchor. Maybe you've got a main line, a belay, and a tag line all tied into the same anchor. The rigging plate makes it much easier to manage that without everything competing for space. So while it may look like a simple piece of hardware, the rigging plate is a great organization and safety tool that keeps anchor systems neat, manageable, and efficient. Rigging plates aren't just about keeping anchor systems neat. They also have some really important specialized uses. One of the big ones is when you're building a mechanical advantage system. As you add pulleys, prussics, and haul lines, the system can get crowded in a hurry. A rigging plate gives you a place to collect all those lines in one spot. That makes the system easier to manage, easier to reset, and safer to operate because you're not fighting with gear stacked on top of each other. Another common use is as the master attachment point in a litter spider. When we're raising or lowering a litter, we often have multiple lines coming into play: main line, belay, tag lines, and spider straps. The rigging plate becomes the central point where all of that comes together before it connects to the litter. It gives us one clean master connection instead of a pile of carabiners clipped together. The same idea applies in a highline system. With all the moving parts, track line, control lines, belay, and haul, a rigging plate provides that single master point where everything is organized and secured. So beyond just organization, rigging plates are key tools for making complex systems functional and safe. Rigging plates are great for keeping systems clean, but because their purpose is to collect multiple points into one, we need to take extra care that we're not overloading the anchor or the plate itself. Whenever you use a rigging plate, think about the total load that's being transferred through it. Multiple connections can add up quickly, and if the anchor or the plate isn't rated for it, you could exceed safe working limits. When selecting a plate, look for one that is NFPA rated G, which means it's designed for general use in rescue loads. That gives you confidence that the hardware can handle the forces we expect in our systems. It's also important that the plate has contoured edges. Sharp or squared-off edges can create wear points on ropes and even damage carabiners. Contoured edges help protect your gear and extend its service life. Finally, check that the holes are large enough to easily accept big locking carabiners. If the holes are too small or the shape doesn't allow for proper seating, you'll fight the hardware every time you clip in, and you'll increase the risk of cross-loading or poor connections. So, the bottom line with rigging plates: choose strong, rated equipment, keep an eye on the loads being applied, and make sure the design supports smooth, safe rigging. Sometimes, a single anchor point just isn't going to cut it. Maybe the anchor isn't strong enough to support the load on its own, or maybe it's not in the right position to line up with the direction of pull. In those cases, we build a multi-point anchor system. A multi-point anchor system collects 2 or more anchor points and brings them together into a single connection point. The idea is to share the load between multiple anchors, so no single one is overstressed. How that force gets divided depends on how you build the system, the connection method, the number of anchors, and especially the angles between them. Another important reason we use multi-point anchors is anticipating failure. Even when we build the strongest system possible, we still have to ask, what if this anchor fails? By combining multiple anchors, we reduce the chance of a total system failure and give ourselves more margin of safety. This works best when the anchors are positioned close to one another, since wide spacing can create odd angles and uneven loading. Now, depending on how the system is rigged, the load connection point can be either fixed or floating. In a fixed focus system, the master point does not move. That makes it simple, but it also means that if the direction of pull changes, one anchor may take more of the load than the others. In a floating system, the master point self-adjusts as the direction of pull changes, keeping the load distributed more evenly. Whichever style you use, once those multiple anchors are tied together, they count as one anchorage. Whether it's fixed and focused or floating, the system is treated as a single anchor from the standpoint of the rope system. So, multi-point anchors are our solution when a single anchor isn't enough. They give us strength, redundancy, and flexibility, but they also require careful rigging to make sure the load is actually shared and not dumped on one unlucky anchor. The simplest way to build a load-sharing anchor system is with just 2 anchors. You take 2 ropes or slings, one tied into each anchor point, and then bring them together into a single focal point. That's done by clipping the ends together with 1 or 2 large locking carabiners. That focal point, the spot where everything comes together, is what carries the load. The idea is that the force is now shared between the 2 anchors instead of being taken by just one. There's also another way to create the same effect. Instead of running 2 separate slings to the focal point, you can stretch a single sling between both anchors and then tie a knot somewhere between them. That knot becomes the new focal point. The nice part about this method is that you can slide the knot placement depending on where the fall line or rope path needs to be. It gives you a little more flexibility in lining things up. So whether you're joining 2 independent slings at a carabiner or tying a focal point not in one sling between anchors, the principle is the same. You're bringing 2 anchors together to share the load and create a clean master point. When we're building a multi-point anchor system, one of the most important factors is the angle between the anchor legs. If the angle is too wide, the load on each anchor increases dramatically. As a rule of thumb, keep the angle 90 degrees or less. At 90, the force on each anchor is still close to the actual load being supported. But once you go beyond that, the numbers climb quickly. By the time you hit 120 degrees, each anchor point is actually seeing a force greater than the original load. That's a dangerous situation and must be avoided. Now let's talk about how the system behaves under load. In a fixed and focused system, the focal point is static. It doesn't move. This works well when the pull is steady and straight, right down the middle. The load is distributed fairly evenly between the anchors. But if the direction of pull changes during the operation, all of a sudden one anchor can end up carrying the entire rescue load. And if you needed a multi-point system in the first place, you probably don't want to dump the whole load back on just one anchor. To help with that, we can use a self-adjusting or load-distributing anchor. This setup often uses a sling tied between 2 anchors in an X, with a carabiner clipped across the X to create the focal point. The advantage is that the master point can shift as the direction of pull changes, keeping the load more balanced. If one anchor fails, the system resets, and the other anchor takes the load. That said, there are trade-offs. If the anchors are far apart, the failure of one can create a shock load on the other. And that's not acceptable in many rescue settings. So self-adjusting systems are best used when you've carefully evaluated the risks and have a way to mitigate them. The takeaway here is simple. Keep your anchor angles tight, understand the difference between fixed and floating focal points, and always consider how your system will behave if something changes or fails. When we talk about redundancy in anchor systems, most of the time it's a good thing. We want backup strength, we want extra layers of protection. But there's a balance to strike. If we keep adding more and more redundancy, the system can become overly complicated, less efficient, and in some cases even less safe. One of the biggest concerns is the possibility of a shock load if part of the system fails. Imagine one leg of the anchor suddenly giving way. The entire load shifts instantly to the remaining anchors. If the system isn't designed to absorb or redirect that shock, it can fail catastrophically. There are a few ways we can mitigate that risk. First, we can build a protected self-adjusting anchor system. Redundancy here means that if any one anchor point fails, the system adjusts to share the load across the remaining anchors instead of dumping it all at once. Second, we can reduce potential fall distance by extending the anchor points closer to the focal point. The less slack and movement in the system, the less energy there is to shock load the surviving anchors. We can also reduce the impact force by shortening the length of the adjusting component. For example, using a sling between anchor points creates a smaller, smoother self-adjusting focal point. High-modulus materials like HMP can slide easily to share the load, though they don't absorb energy well. A cordelette or nylon sling may not slide as smoothly, but it helps absorb energy if one anchor fails. When done correctly, this type of system has some real advantages. The load remains distributed among the anchors, even if not perfectly equal. And if one anchor does fail, the system should adjust and continue to function without creating an excessive shock load on the remaining points. So, redundancy is important, but it's only effective if it's built smartly. Too much complexity slows you down and can compromise safety. The goal is always balanced redundancy that protects the system without making it unmanageable. Let's talk about self-adjusting anchor systems, which are sometimes also called self-equalizing systems. First off, it's important to clear up a myth. There's no such thing as a truly self-equalizing anchor system. No matter how you rig it, the forces on the system will never be perfectly balanced. The angles, the material, and the way the load shifts all mean that one anchor will always take more than another at some point. Another limitation is how these systems behave under shock loading. If one anchor fails, the system doesn't instantly rebalance. During that moment of adjustment, some of the surviving anchors will see a sudden spike in force, and that's where things can get dangerous. Now, this doesn't mean self-adjusting systems have no place in rescue. Used carefully, by trained rescuers, they can be a valuable tool. But there are guidelines you need to follow. Keep the angles small. The tighter the angle, the less force magnification you put on each anchor, and the easier it is for the system to readjust safely. Minimize slack. Design the system so that if one anchor fails, the drop is as small as possible. Ideally, less than a foot. Use slimmer materials for the adjusting component, so knots won't jam through carabiners when the system resets. Be careful with high-tech fibers like Kevlar or Spectra. They're strong, but they don't absorb shock well. If you use them, you need other shock-absorbing elements in the system. Make all anchors as bomb-proof as possible. If you're relying on a self-adjusting system, you don't want weak links. Keep anchors close together. If they're too far apart, not only do the angles get wider, but if one fails, the shock load on the other becomes much higher. A good rule is to keep the outside angle, from the outer anchors down to the focal point, below 90 degrees, and ideally closer to 60. The key message here is that multi-point anchor systems are not for casual use. They require skill and a clear understanding of how forces are shared, and sometimes multiplied, within the system. If you get it wrong, you could overload the entire setup or one of its components, leading to catastrophic failure. So, self-adjusting anchors aren't off limits, but they're a high-skill tool. Use them only when the benefits outweigh the risks, and only when you're confident you can control the variables. Next, let's look at directionals. A directional, sometimes called a deviation, is simply a way of moving the rope into a more favorable position or angle. Think of it as guiding the rope so it runs where you want it, not where gravity wants to pull it. You can create a directional in lots of different ways. Off a tree, a piece of hardware, or even a purpose-built directional pulley. Each option has pros and cons, and you need to judge which one fits the situation best. One of the big reasons we use directionals is edge protection. A loaded rope running across an unprotected sharp edge can be damaged very quickly, and that's one of the fastest ways to lose a system. By rigging a directional, we can pull the rope away from edges or redirect it to where edge protection is more effective. Another key factor is the location of your directionals. Anchor points for these need to be safe, solid, and accessible for rescuers to rig and check. If your directional is in a spot where the team can't reach it easily, or it forces them into a dangerous position to set it up, then it's not the right choice. So, the main takeaway is, directionals are about rope management. They let us set the angle we want, avoid hazards, and protect the rope, but only if we place them smartly and safely. Let's talk about back tying. This is a really practical technique for those times when you've got a good anchor position, but the anchor itself just isn't strong enough on its own. For example, picture the anchor point on the edge here. It's in the perfect spot, right where you want the rope to run, but it doesn't have the strength to handle the full rescue load. Instead of discarding it, we can treat it as the primary anchor and then connect it to a secondary anchor behind it. Together, the two anchors can safely share the load. That connection between them, whether it's rope or webbing, is what we call the back tie. And there are two critical things to remember about it. 1. The back tie anchor has to be as strong as or stronger than the primary. If it's weaker, you haven't really improved anything. 2. The back tie must be free of slack. If there's slack and the primary anchor fails, you'll get a shock load when the system suddenly shifts, and that can take out both anchors at once. Now, this is where pretension back ties come into play. Rope stretch and anchor flex can leave a little bit of slack in the system, even if you think you've tightened everything up. To prevent that, we pretension the back tie before loading it. One simple way to do this is with a small mechanical advantage system. You pull the back tie tight, remove the slack, and then secure it in place. That way, if the system is loaded suddenly, everything is already snug and less likely to shock load. So, back ties give us a way to use anchors that aren't strong enough alone by tying them together. But they only work if the secondary is solid and the system is kept tight. When we're out in the field, one of the most important skills for a rope rescuer is being able to quickly identify and evaluate potential structural anchorages. In many cases, especially in urban or industrial settings, we won't have pre-planned anchor points. So it's on us to size up what's available and decide if it's safe. In natural environments, it's pretty straightforward. Boulders and large, healthy trees are the go-to anchors. But in cities, construction sites, or buildings, those options disappear. That's when we have to think in terms of structural elements of the building itself. Examples of solid urban anchor choices include structural columns, projections of structural beams, supports for large machinery that are designed to carry heavy loads, stairwell support beams, brickwork with bulk, like a solid corner wall, and anchor systems built into buildings for window cleaning equipment. But not everything you see is safe. Some things look tempting, but they won't hold up under load. Examples of inappropriate anchors include corroded metal or rusty pipes, weathered stonework that's already crumbling, brickwork with deteriorated mortar, thin sheet metal vents, gutters and downspouts, those are for water, not rescues, small brick features like chimneys without bulk. And yes, even fire hydrants or standpipes, they look tough, but they're not designed to take rescue loads. The bottom line, good anchors are structural, solid, and built to handle large forces. Bad anchors are corroded, decorative, or lightweight features that might hold body weight, but won't hold a rescue load. Remember, just because it looks strong doesn't mean it is. Always evaluate carefully before you clip in. Now, let's talk about less obvious anchorages. Sometimes you'll look at a building and think, there's nothing here I can use. But with some practice and a good eye, you'll start spotting options that aren't immediately obvious. For example, elevator or machine housings on rooftops. These are often much larger and stronger than they look. By wrapping rope around them several times and finishing with a figure-8 bend, you can create a solid anchor point capable of holding multiple lines. Another option are scuppers, those roof drain holes you'll see at parapets. You can run rope or webbing through the scupper and over the parapet to form an anchor. But here's the caution. Reinforced concrete parapets are best. If it's brick or block, you'd better check the mortar carefully, and even then, back it up with another anchor. And of course, pad every sharp edge. Ropes don't like sharp corners. You can also use wall sections between windows or doors. If you've got two openings close together, you can pass your rope or webbing through one, around the wall, and out the other to build a very strong anchorage. Again, Place it on the side opposite where your rope is running. It keeps the work area cleaner and safer. Stairwell beams are another go-to in buildings. Just make sure you're tying into the actual structural steel, not something decorative. Finally, there are installed anchorages, and these are the gold standard when you have them. Some industrial sites and newer buildings have permanent, engineered anchors designed for window cleaning or confined space entry. If they're certified and documented, they're usually bomb-proof. But don't confuse them with things like guy wire hooks. Those are for antennas and signs, not for holding people's lives. Even with installed anchors, remember, many are designed for vertical loading, and they might fail if pulled sideways. Best practice is to always back them up. So, the lesson here, don't stop at the obvious. With creativity and good judgment, you'll often find anchors hiding in plain sight. Sometimes, you'll find yourself in a spot where there just aren't any obvious anchor points. That doesn't mean the job stops, it means we adapt. One option is extending anchor points. If there's nothing strong nearby, you can run static rope, sometimes even hundreds of feet, out to where suitable objects exist. Think of a rooftop with nothing usable on top. You might run rope down a stairwell, or out a window to get to something solid on a lower floor. But here's the catch, you've got to use static rope. Polyester static ropes are even better than nylon because they stretch less. Dynamic rope, on the other hand, would be dangerous here. Too much stretch, too much bounce. And even with static rope, you may need to double or triple the lines to keep the system from sagging under load. Another method is using vehicles as anchors, something we see a lot in fire and rescue. Fire engines, rescues, or other emergency vehicles can serve as portable anchorages, but we need to be smart about it. Vehicles aren't designed as anchors, so conditions matter. Always park on solid ground, set the brake, and if it's a manual, put it in gear opposite the pull. Don't forget to chock the wheels. Even big rigs can slide under load. If no chocks are handy, spare tires work in a pinch. And make the setup error-proof. Pull the keys and flag the cab so no one drives away while you're tied in. When attaching, aim for structural parts like axles or cross members. Avoid tow hooks, bumpers, or anything that looks convenient but isn't truly structural. Those parts can rip off under load, and you don't want that happening mid-rescue. Also, watch for hazards like hot exhaust, oil, grease, or battery acid. All of those can damage rope or webbing if you're not careful. Bottom line, vehicles can work, but only if treated with the same respect as any other anchor. Check, double check, and make sure it's bomb-proof before you put a rescuer's life on that system. Now let's talk about where you actually place your anchor systems. At the end of the day, no matter what gear you have, good placement comes down to good judgment, and that only comes with practice and experience. All anchor systems share a few common characteristics. First, don't just think about the strength of the anchor itself. Think about how safe and accessible it is for rescuers who will be working with it. An anchor that's strong but positioned in a way that puts rescuers at risk isn't a good anchor. It's also best practice to set your anchorage connector as close as possible to a structural connection point. That minimizes torque and leverage on the system. Think of a fence post. It's much stronger near the base where it's set into the ground than it is halfway up. Same with trees or vertical columns. That said, there are times when anchoring higher up makes sense. Maybe you're trying to create a better angle for an edge transition, reduce abrasion over a sharp edge, manage a loaded litter more smoothly, or even reduce friction on a mechanical advantage system. In those cases, mid-span or higher placement can actually be the better choice. But again, it's about balancing safety, efficiency, and system strength. So, judgment is the name of the game here. And just like anything else in rope rescue, the more you practice evaluating anchor placements in real environments, the sharper your judgment becomes. Before we ever put a live load on an anchor system, we need to run a safety check. Think of this as your final line of defense, a quick but thorough evaluation that can prevent a catastrophic failure. Start with the system components. Are your knots tied correctly and dressed cleanly? Are all carabiners oriented the right way and locked? I always tell my crews, if you can't confirm it's locked, assume it's open. Next, check the overall strength of your anchor points. Each one should be strong enough for its share of the load, with a margin of safety. If there's any doubt, back it up or don't use it. Then look at the configuration and alignment. Put a little tension on the system. Not a full load, just a nominal pull in the intended direction. Watch how the anchor system reacts. Are the legs taking load the way you expected? Are the angles staying safe? If something shifts under a small pull, it's going to fail under a real load. Finally, check the condition of the anchor and connectors. Is the tree alive and solid? Is the beam free of rust or cracks? Is the webbing or rope free of cuts, burns, or soft spots? Even the strongest rigging in the world will fail if it's built on rotten material. Bottom line, this check only takes a minute, but it can save lives. Treat it like your pre-flight checklist, don't skip it. Alright team, let's bring Chapter 11 on anchors to a close with a quick summary. First, language matters. We've all worked with people from different industries: fire, construction, climbing, rope access, and each one has its own vocabulary. Standardized terminology keeps everyone on the same page and keeps us safe. Second, strength matters. Every anchorage we choose has to be capable of withstanding the maximum anticipated load, plus a safety factor. That strength depends on the condition of the anchorage, its structural design, and exactly where and how we place the load on it. Third, location matters. Anchors work best when they're directly above and close to the load. If the anchor isn't in the right place, you can lose efficiency and increase risk. Fourth, backup matters. Anchors are the foundation of the whole rope rescue system. If they fail, everything else goes with them. So, backing them up, whether with the same anchorage or a completely separate one, is just smart practice. We also covered the different types of systems. Single-point anchorages, like tensionless hitches, knots, slings, and straps. Portable anchorages, prefabricated systems you can move like beam clamps, picket systems, or even tripods. Rigging plates, those little pieces of hardware that keep our systems neat and prevent cluster headaches. Multi-point systems, fixed and focused or self-adjusting setups that distribute the load across several anchors. Directionals, those midline anchors that change rope direction for safer or cleaner rigging. Back ties, reinforcing an anchor that's in the perfect spot, but not strong enough alone. Structural anchors, everything from natural boulders to building columns. And finally, if nothing else is available, extended anchors or even vehicles, with caution. And remember, before you load the system, check it. Check your knots, your carabiners, your alignment, and your anchor's condition. One last look can prevent a tragedy. Anchors don't fail often, but when they do, they don't send warnings. Back them up, check them twice, and trust them like your life depends on it. Because it does.